Let's work on some exercises in section 14.5. We start with, I think for this part here, I will do number 4 and number 6. Number 4 first. We get C equals to tangent inverse of phi over x, where the x equals to e to the t, and then y equals to 1 minus e to the negative t. And we want to find dc dt. So c is a function of x and y, both of them function of t. So dc dt is the partial of c respect to x first, and then derivative of x respect to t, plus the partial of c respect to y times the derivative of y respect to t. This will give us derivative respect to x, that will be 1 over 1 plus y over x squared, and derivative of that respect to x will be negative y over x squared, right? That's the dou c dou x, times dx dt will be, which is e to the t, plus dou c dou y will be 1 over 1 plus y over x being squared times 1 over x times e to the negative t. Okay, now the first term give me negative of y e to the t over x squared plus y squared, plus the second one I will get x e to the negative t over x squared plus y squared. I multiply the top and the bottom by x just to make it even at the denominator, right? We have x squared on the denominator to multiply by. Okay, so now I think we can put them together. This is then equal to x squared plus y squared on the denominator, x e to the negative t minus y e to the t. Okay, that's for number 4. Number 6. We need dw dt. So w is a function of x, y, z, and each x, y, z function of t. Okay, so dw dt will be dou w dou x, and then dx dt plus dou w dou y times dy dt, and plus dou w dou c dc dt. Okay, so the derivative of that is, oh, you know what? This is actually 1/2 natural log of x squared plus y squared plus z squared. Is it right? Okay, so the derivative of that will be 1 over 2 times x squared plus y squared plus z squared times 2x, times the derivative of x respect to t, that's cosine t, plus dou w dou y, that will be then 2y over 2x squared plus y squared plus z squared, and then negative sine t. And then plus, similarly, derivatives tangent t is this is 2c over 2 times x squared plus y squared plus c squared times secant squared t. So I think I can cancel the 2. So I get x cosine t plus y minus y sine t plus 2c secant squared t. No, actually the 2 cancels over x squared plus y squared plus c squared. Actually, I happen to see this that x is sine t. So you will see that this is actually xy minus xy plus z secant squared t over x squared plus y squared plus c squared, right? And the xy cancels. So we get c secant squared t over x squared plus y squared plus c squared. Okay, let's see next. Number 10 maybe. Number 10, find dou c dou s. So dou c dou s equals to dou c. Let's see. C is a function of x and y. X and y, both of them function of s and t. Okay, so dou c dou s will be dou c dou x times dou x dou t plus dou c dou y times dou y dou t. So dou c dou x for this guy, that will be just itself, huh? E to the x plus 2y times negative s over t squared plus dou c dou y, that will be 2e to the x plus 2y dou y dou t. That's 1 over s. Yeah, if I factor e to the x plus 2y out, then I will get a 2 over s minus s over t squared. You can do the LCD thing if you want to, but actually, in my opinion, it's good enough there. Okay, now then how about dou z dou t? Dou c dou t, partial of c respect to t, will be dou c dou x times dou x dou t plus, oh, hold on. I think I make mistake, buff. My bad. I'm actually doing this. This is, you know what? What am I doing? That's a wrong notation. So let's do this. This is dou c dou t then. Okay, now I'm about to do dou c dou s. I just realized that. Where's my mind so far? So this is dou c dou y dou s. Okay, so we have e to the x plus 2y times dou x, that's 1 over t plus 2e to the x plus 2y. Derivative respect to s is negative t over s squared. I factor e to the x plus 2y out. 1 over t minus 2t over s squared. That gives us e to the x plus 2y, and then s squared minus 2t squared over s squared t. Interesting. Quite similar, huh? With the with the dou c dou t. Anyway, that's for number 10. I wonder if you can try number 12 yourself. Well, I do it. Number 12. Z is a function of u and v, but then u, v are both function of s and t. So dou c dou s, I need to be careful now. Don't make the same mistake twice. Dou c dou u times dou u dou s plus dou c dou v times dou v dou s. Now, by the way, be very careful when you write your v and u. Okay, make sure you have a way to differentiate them. Like the one I have here, my u have a tail, my v does not have. You know, some people write their v like a u, right? Your v looks like a u maybe. Be careful with that. Okay, let's see. So dou c dou u, the derivative of tangent is secant squared u over v times derivative with respect to u, that's 1 over v, and then dou u dou s, that's 2, plus dou c dou v, that is secant squared u over v times negative u over v squared times derivative of v respect to s, that's 3. I think we can factor 1 over v out. So secant squared u over v times 1 over v parentheses 2 minus 3u over v. You know what? Let me factor another one v from the denominator. Okay. Now then, how about dou z dou t? That will be dou c dou u times dou u dou t plus dou c dou v times dou v dou t. This is secant squared u over v times 1 over v times 3 plus dou c, that will be secant squared u over v times negative u over v squared derivative respect to t, that's negative 2. So I will factor 1 over v squared secant squared u over v, that's 3v plus 2u. Okay, that's for number 12. Let's go on. Here we have a larger one. Okay, let's do number 24. So we have that function p as a function of u, v, w, and each of them functions of x and y. What we need are dou p dou x and dou p dou y. Let's do dou p dou x first, and we will plug in x equals 0, y equals to 2. Okay, let's compute that first then. How about u 02? u02 is 0. v02 is 2, and w02 is 1. Okay, so dou p dou x will be dou p dou u times dou u dou x plus dou p dou phi times dou phi dou x plus dou p dou w times dou w dou x. Oh, the partial with respect to u and phi and w seems to be all similar, huh? That's u over square root of u squared plus phi squared plus w squared times e to the y plus phi over square root of u squared plus phi squared plus w squared times respect to x, that's y e to the x plus w over square root of u squared plus phi squared plus w squared respect to x, that will be y e to the xy. Okay. Let me factor something out then. So this will be u e to the y plus phi y e to the x plus w y e to the xy over square root of u squared plus phi squared plus w squared. Now, so what is the dou p dou x for x equals to 0 and y equals to 2? Okay, then I basically plug that in, right? This is 0 squared plus 2 squared plus 1 squared. On the numerator, I will have 0 e squared plus the phi is 2, the y is 2, the x is 0 plus w is 1, the y is 2, e to the x, that's also 0. Okay, so that is 4 and then 6, that's 6 over square root of 5. It's 6 radical 5 over 5. Okay. Notice that I substitute the u phi w from that when I plug in 0, 2 in there. Next, how about dou p dou y? You will see it's very similar, supposedly, right? That will be dou p dou u dou y plus dou p dou phi times dou phi dou y plus dou p dou w times dou w dou y. That's u over square root of u squared plus phi squared plus w squared. Respect to y, that will be x e to the y plus phi over square root of u squared plus phi squared plus w squared. And then respect to y, that's e to the x plus w over square root of u squared plus phi squared plus w squared times the derivative of e to the xy respect to y, that's x e to the xy. Let me put them together first. U, by the way, we happen to know x e to the y, that's u, that's u squared plus phi e to the x plus w squared x. Don't you think it's actually easier if you happen to see that, right? So dou p dou y at x equals to 0, y equals to 2 is, the u is 0, the phi is 2, the x is 0, w is 1, the x is 0 over square root of 5. We know that square root of 5 earlier. So this is 2 over square root of 5, which is 2 square root of 5 over 5. Okay, so I think at this point you should be able to see the principle behind this. Okay, it's just routine, right? So I do only one problem here. I was planning to do number 26 also, but I think once you get used to it, and notice that I will always start from this, the diagram. Okay, it helps you to visualize how will you do the partial derivatives. Let's go on. Use equation 6 and then use equation 7 to do the derivative or partial derivative. If you remember, equation 6 in this section refers to implicit implicit differentiation theorem. Okay, which basically says that if we have f x y equals to the constant, then the partial of y respect to x is equals to negative f sub x over f sub y. If we have f as a function of x, y, z, then the partial of c respect to x is negative f sub x over f sub c, and partial of c respect to y is negative f sub y over f sub c. When I went over sections 14.3, I unintentionally thought that we already learned this, so I used this formula. Okay, but that's what actually happened. So let's see number 28, for example. We set let fxy equals to cosine xy minus sine y equals to 1. Basically, you change that equation, okay, make one side equals to constant and the other side, which with variables, you call that the function. Okay, so you call this the function of this, which you set equals to a constant. Okay, it doesn't have to be 0 though. Okay, it doesn't have to be 0. The way our textbook does it seems like they insist to be 0, but it's actually no, not necessary. Okay, now then the partial with respect to x is negative y sine xy, and partial with respect to y will be negative x sine xy plus cosine y. So dy dx, that's what I meant here, dy dx will be negative of f sub x over f sub y. Okay, the negative cancel with the top. I get y sine xy over cosine y minus x sine xy. Okay, let's try again. Number 30. You will see this is basically just a routine though. Let function fxy equals to e to the y sine x minus xy. Set it equals to constant 0. So f sub x will be e to the y cosine x minus 1. F sub y will be e to the y cosine x. Oh, I'm sorry, minus y here. Now here I will have minus x. So dy dx will be negative of f sub x over e to the y cosine x minus x. I think that's simple enough, huh? Now, how about number 32? Number 32, let f x y z be x squared minus y squared plus z squared minus 2z, and you set it equals to constant. So f sub x equals to 2x, f sub y equals to 2y, negative 2y, I mean f sub z equals to 2z minus 2. Therefore, dou c dou x will be negative f sub x over f sub c. Cancel the 2, we get negative x over c minus 1. Dou c dou y will be negative f sub y over f sub c. That will be y over c minus 1. Okay, a lot simpler, right? A lot simpler. Number 34, let's do that. Number 34, let function f be a function of x, y, z equals to yz plus x natural log of y minus c squared. Okay. Some space. So f sub x will be natural log of y. F sub y is c plus x over y. F sub c is y minus 2z. Therefore, dou c dou x will be negative f sub x over f sub c. Let me reverse the order subtraction on the denominator to absorb the negative. Dou c dou y is negative f sub y over f sub c. I reverse the order of subtraction on the denominator to get rid of the, I absorb the negative by reversing the order subtraction on the denominator, and then I multiply the top and the bottom by y. So I get x plus yc over 2yc over y squared, minus y squared. Okay, that's for number 34. I think next we go to application. The radius of a right circular cone is increasing at the rate. Let's see first. Circular cone. I hope you all know what's the formula. At this point, I do expect you to memorize the formula for some basic trigonometry. Like the volume of a cone is 1/3 area of the base. Area of the base times height. In fact, this is true for any pyramid. Okay, regardless what's the base look like. Regardless what's the base look like. Okay, as long as you have that base and then the top is just a vertex, then the area or the volume is equal to 1/3 the area of the base times the perpendicular height. Okay, it is always true. It is always true. So here we have 1/3 area of the base times the height, right? Area of the base is pi r squared times the height. Now, the thing is we have this situation. The radius is increasing at 1.8 inches per second. So the change of the radius respect to time is 1.8 inches per second, while the height dht is decreasing at the rate of negative 2.5 inches per second. Now the question is, at what rate is the volume of the cone changing when the radius is, the r equals to 120 and the height is 140 inches. Okay, so what we want is d phi dt. Notice that phi is a function of radius and height, each of them function of time, right? Okay, so d phi dt will be dou phi dou r dr dt plus dou phi dou h times dh dt. That will be 2 over 3 pi r h times dr dt plus 1/3 pi r squared times dh dt. Now let's plug in number. I think I want to factor the 1/3 pi out, 1/3 pi r out. So I get 2h dr dt plus r dh dt. And then from there I plug in numbers. The r is 120. Notice that, let's keep the units so that you can see why we have the change of volume over time. This is inches, 2 times 140 inches, and then the r dt is 1.8 inches per second, plus the r is 120, dh dt is negative 2.5 inches per second. Notice that the units, if we play all the way, it will be inches cubed per second, right? 2 times 140, that's 280 times 1.8. So 28 times 18, 4, 6, that's 22, 28, that's 504. Plus, it's actually minus 4, 2.5. So divided by 4, 3 becomes 300 minus 300 cubic inch per second. So that will be 204 times 4, that's 816 pi cubic inches per second. That's the change. Okay, and from here we see that the volume is actually increasing. The volume is actually increasing. Think of this. I remember I have this kind of question when if you happen to know, there's one time many years ago we have oil leak from in the Gulf, Gulf of Texas. There's some oil leak at some of the oil exploration place, what you call it. So basically, it's under this. So let's say this is the rig, right, on the sea. Okay, and then we have the oil leaking from the bottom. Now, what they know is then how do we compute the amount of oil leaking at that time? So we see the radius here, okay, and then we also know that originally it looks like a cone, right? Okay, it looks like a cone. Now the radius increases. Of course, oil is lighter. The density of oil is less than the density of seawater, right? So what happened then, the radius at the surface of the ocean, the surface of the oil seems to be increasing. Not perfect circle, however, but we can approximate that by a perfect circle. Okay, but then we know that it already the the depth is actually decreasing. So the question is, what is the volume? How much the volume actually changes? From there, they can more or less compute how much actually still leaking at the bottom. At the bottom. Okay, so at the original leaking, it looks like the blue, the purple color here. But then, as they try to stop the leaking, okay, so what happened is they still have some leaking here, though, right? They still have some leaking there. Okay, but the cone is not as deep anymore. Okay, so they may have a small leaking at the bottom. Okay, now once they already uh, reduce the leaking, they can see how much actually it is, how much leak it has. Now imagine if the leaking has not been stopped. Okay, so the depth stays the same, but the radius increases, right? Now we still can compute how much oil actually leaking, how fast it is actually leaking. Okay, we approximate the oil that is leaking as a cone. Of course, it's not a perfect cone, but it can be approximated. Okay. Let's do a bit more. Let me erase that. It's just some historical background that I suddenly have in mind when I did this problem. You know, people was wondering, oh, how do they know how much oil, how fast the oil is actually leaking? Because nobody should be under the water at that time. In fact, those people already run away from the oil rig, right? Okay, so how do they know how fast the oil is actually leaking? By seeing how fast the radius of the base of the inverted cone, how the radius of the base of the inverted cone actually increases. And if we have not stopped the leaking, means the depth of the cone to the source of the leaking stays the same. Okay. Now you may wonder, but Thomas, what happened if we have some current? So of course, then the cone may not be that perpendicular anymore. Yes, it's not perpendicular anymore, but the formula actually stays the same though. So maybe the center of the circle is actually not at the perpendicular projection. Okay, but the formula is still the same. The area of the base multiplied by 1/3 the height. Okay. That's for number 38. Let's see number 46. I want to go over this. This is an odd number, as you can see, but I want to go over this especially because it has something to do with what we have later on when we do surface area. Okay, now notice that the z is a function of x and y, but the y, x and y here is basically the polar. In polar, we convert that to polar. Okay, so what happened with dou c dou r, dou c dou theta, and show that this thing. Now notice that you will see later on that this guy here has something to do with the surface area. Okay, has something to do with surface area, and you will then see this is something to do with surface area from polar coordinate system point of view. Okay, let's work it out. I think that's quite easy. For z sub, so you see z is a function of x and y, but x and y function of r and theta, right? So dou c dou r will be dou c dou x times dou x dou r plus dou c dou y times dou y dou r. Unfortunately, we don't know what is the f, so the best we can say is this is c subscript x times dou x dou r will be cosine theta plus c sub y sine theta. Dou c dou theta will be dou c dou theta will be z sub x times negative r sine theta plus z sub y times r cosine theta. Okay, and we want to show that c sub, so we are done with part A. Now how to do part B. Notice that honestly I don't really know how to do this one though, but I think notice that this is actually equals to negative y c sub x plus x c sub y, while this one here is z sub x times x over r plus the c sub y times y over r. Not that I think it helps. But then let's see. So dou c dou r squared is equal to c sub x x over r plus c sub y y over r being squared. That is x squared c sub x squared over r squared plus 2c sub x c sub y xy over r squared plus y squared c sub y squared over r squared. They're all over r squared, huh? They're all over r squared. So this is equals to x squared c sub x plus, you know what? I think I can rewrite it as, what am I doing? No, I'm actually, you know what? Let me rewrite it this way. It's nicer. Z c sub x c sub x plus y c sub y over r squared, over r being squared. That is something over r squared. Let me just leave it like that for now. Now, how about dou c dou theta? Dou c dou theta. We have common factor r, huh? Actually, we have this. Okay, so that is xc sub y minus yc sub x squared, right? Now then this will give us x squared c sub x squared plus 2xy c sub x c sub y plus y squared c sub y squared over r squared. Now this will be x squared c sub y squared minus 2xy c sub x z sub y plus y squared c sub x squared. If we divide this by r squared, that's what we get. And therefore, if we add them, dou c dou r squared plus 1 over r squared dou c dou theta being squared, we basically add those two terms. This guy with this guy added together. Okay, so we get x squared c sub x squared plus 2xy c sub x c sub y plus y squared c sub y squared plus x squared c sub y squared minus 2xy c sub x c sub y plus y squared c sub x squared. Now notice that we have two terms cancel in the middle, right? That one is not too hard to see, but then notice that we have x squared plus y squared c sub x squared plus x squared plus y squared z sub y squared over r squared. Now that is x squared plus y squared c sub x squared plus c sub y squared over r squared. But remember, x squared plus y squared equals to r squared, right? As we expect. I think this is the last question. Oh, in fact, this is actually the same with the same setup, huh? The same setup. Find dou c dou r, which we did. Dou c dou theta, which we did, right? Dou c dou r. Let me copy paste that. Lazy. I'm lazy. Copy and then paste. Make sure I'm not missing anything. I'm missing the dou here. Okay, now then. Yeah, the thing is I simplified this way already, which may not be necessary. Let me just leave it like this. Okay, let me just leave it like that. So, what is dou squared z over dou r dou theta? Assuming continuity, this is just the same to z subscript theta r, which is the same to z subscript r theta. Okay, so I will use basically z sub r c sub r and do the partial respect to theta. Okay, now let's break it up first. This actually consists of two parts, right? So I will do partial respect to theta of z sub x cosine theta plus the partial respect to theta of c sub y sine theta. Actually, I don't really need to do this, but I want to make sure that you know the flow. I will change my color so that you can follow the flow. I will use the purple one for the first part here. And later on, I will use the magenta, you call that, or maybe pink for that one. Okay, let's do this first. Now, this is, remember, I will do product rule, right? So this is dou c sub x dou theta cosine theta plus c sub x times the derivative of cosine theta respect to theta, that's negative sine theta, plus dou c sub y respect to theta sine theta. Oh, sorry. I should change the color, huh? I should change the color. So plus dou c sub y over dou theta sine theta plus c sub y cosine theta. This way, I hope we can keep track of the work, right? Now, the difficult part is dou c sub x dou theta is what? Well, we're supposed to do it this way. So we're supposed to do the chain rule again. So c sub x respect to x dou theta plus dou c sub x respect to y dou theta cosine theta plus c sub x, make it minus, sine theta plus, change color, the partial with respect to y. So maybe I want to say that yeah, this guy here becomes this. Okay, and then later on this guy here becomes this. Dou c sub y dou x dou theta plus dou c sub y dou y times dou y dou theta times sine theta plus c sub y cosine theta. Painful, huh? But anyway, this is equal to z sub xx times dou x dou theta is negative r sine theta plus c sub xy dou y dou theta is r cosine theta times cosine theta minus c sub x sine theta plus this is c sub yx times negative r sine theta plus c sub yy r cosine theta sine theta plus c sub y cosine theta. It was defined, yeah, defined as usual. So this will then be negative r sine theta z sub xx plus r, oh, I still have cosine out there, cosine theta z sub xx plus r cosine squared theta c sub xy minus c sub x sine theta, and then negative r sine squared theta c sub yx, which is the same to xy. Like I'm doing this times this. And then this guy is plus r sine theta cosine theta z sub yy, and then plus c sub y cosine theta. I wonder if you will understand if I do some kind of combination. I think we can just stop here, but I want to show you the following. Notice that this guy is actually negative r over 2 sine 2 theta z sub x, or maybe no, I don't want to do it that way. I will multiply the top and the bottom by r, so I multiply by r and divide by r, multiply by r, divided 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 by r. My purpose is so that you see r sine theta, r cosine theta, that's basically xy, right? Negative xy c sub xx minus over r plus x squared over r c sub xy minus y z sub x over r plus xy c sub yy over r minus y squared c sub xy over r plus x c sub y over r. Okay, if I put them together, that's 1 over r negative xy c sub xx. Okay, I want to mix this guy and that guy, plus x squared minus y squared c sub xy plus c sub yy plus xy c sub yy. And then plus xc sub y minus yc sub x. Whew. Will that simplify to that, or should we just stop here and simplify it? It depends on how far you want to go. Okay. Notice that I still have my r, but I don't have the theta anymore, at least, right? Okay. In other words, the mixed partial derivative of a function, when you do the partial derivative with respect to components in polar, it will not be dependent on theta. Okay, I mean, unless it if you see that from x and y, right? Okay, I guess I should not say that way, but I mean, from the formula you see that you can get rid of the theta it depends on x and y instead. Okay, that's for now.